Good morning, and again, it's a great pleasure to be here at the 20th anniversary celebration of the Keck Observatory. I've been assigned to discuss what I believe has been one of the most influential areas, what's up with the resolution, of the Keck telescope, known as the intergalactic medium, the gas between galaxies. It's an area that's really benefited, as you'll see, from both the aperture and the high-performance instrumentation of the Keck telescopes. I'm going to dedicate this talk to two scientists who really drove a lot of the science that I'll be showing. Walt Sargent on the left from Caltech, who passed away last year, and Arthur Wolf on the right from the University of California, San Diego, who I hope is listening to this webcast. It's fair to say they really drove a lot of the science in this topic of the intergalactic medium, and it's also fair to say that this first-year graduate student wouldn't be standing here without their support over the years. So the intergalactic medium these days is more commonly referred to as the cosmic web, and Sandy in her talk showed a couple of very nice movies of the cosmological formation of galaxies. I'll show you some of the outputs of some other simulations, again performed on high-performance supercomputers, visualized with pretty colors. What you're seeing is the universe on large scales. Galaxies in these images are just little dots. And you see filamentary-type structures driven by gravitational collapse that leads to this so-called cosmic web appearance of our universe. Large scales, many galaxies here again would be just little dots in the image. And it's the cosmic web, it's this filamentary structure which I'm talking about today. These are visualizations from the computer. As I stand before you 20 years of Keck's, despite its terrific aperture and great success, we don't have pictures like these of the cosmic web. These only can come from computers today. But we've learned a lot about the cosmic web, as you'll see. And we have ideas on how we may generate images like these during the next 20 years of the Keck telescope, which is where I'll finish this talk. Now, when I started 20 years ago on research, the model that we had for the cosmic web was something more like this: amorphous clouds of gas between and around galaxies. I'd say this is the intergalactic medium before Keck. And again, it's because we don't have direct images of the cosmic web that we had to really struggle to develop this picture, this paradigm that exists today. The technique that we use is a somewhat unique one to astronomy. We call it the Absorption Line experiment, and we do science in silhouette. Most of the time we're not studying the objects, we're studying the lack of light associated with a given object, as I'll now describe to you. Science in silhouette. So we have the cosmic web, the intergalactic medium that we're interested in studying, some gas in the distant universe. We have a large telescope, that's great. And the trick that we use, really, is to identify a bright background source, typically quasars, supermassive black holes that are shining towards us here on Earth. Most of the light from that quasar comes to us, and we receive it at the telescope. But depending on what this cosmic web is made out of, some of that light is absorbed, scattered, and heads off in some different direction, and we don't see that material. That's what I mean by doing science in silhouette. Let me dig in a little further. This is a spectrum of a quasar, idealized spectrum, wavelength on the x-axis, intensity here on the y. Some emission from hydrogen, that's what this peak is here. Some emission from carbon over here, some emission from silicon. Now we'll put some gas in the way, a cosmic thread. If there's atomic hydrogen in that gas, then you will know from your freshman physics class that it will absorb light at specific frequencies, specific wavelengths, including 1215 angstroms. And so that light is scattered away, and you see now this absorption feature. Let me zoom in on that. That's what we call an absorption line. And it's the study of features like this which lead to all the science that I'll be describing today. Let me go one level further. As Sandy mentioned, the universe is expanding, as she showed in her movies. This leads to a cosmological redshift. That's something that we actually get to use to our advantage. Here's that same quasar spectrum, but now it's been redshifted. The wavelengths shown here are at larger wavelengths in the optical, which we can observe with Keck. And if there's a cosmic web in the way, say at a redshift of 4, it'll absorb gas at this wavelength, around 6,000 angstroms. If there's another patch of the universe closer to us at a lower redshift, it'll impose absorption at a different wavelength, a shorter wavelength. And yet closer gas, shorter wavelengths still. In the real universe, of course, is far more complex than what this cartoon is showing, and here's now actual data from the Keck telescope. You see a true forest of absorption lines. We refer to this as the Lyman-off of forests. As you'll see as I go along, this is the cosmic web in spectroscopy. Now, we're here to celebrate the Keck telescope, and you've heard a number of reasons for why one builds large aperture telescopes. One of these is to observe the universe at very high angular resolution, or in this case, the center of our galaxy. Some of us use the telescope to study bright objects at very high precision, studying motions on meters per second, and you'll hear following talks science that's studying the faintest objects at the very edge of the universe. Well, we IGM scientists, we like to have it all. So we observe the very faintest objects that we can find at the very highest precision. And if the very sharp engineers and scientists that give us AO would do so, we would even use it in the optical, because the objects we tend to study are also very small, point source type objects. This is a spectrum with a Keck ESI spectrometer, high precision data of an object really towards the very edge of our universe. That, of course, means we have tremendous exposure times here to the longest exposed objects with the Keck telescope, a day and a half worth really of direct observations. This object, I'm told, was once observed all night long, that is from sundown to sunrise. The operator acquired the objects, and the observers observed it all night long. Indeed, we're the most efficient observers at the Keck telescope. Now, I said the science really flows from the aperture of the telescope, the 10-meter aperture. It also flows from state-of-the-art instrumentation. The data I'm showing you comes from two optical spectrometers, high-resolution spectrometers designed and manufactured at the University of California Observatories, UCO. I also wanted to give a nod to one of these so-called unsung heroes of the instrumentation world. We heard quite a bit about Keith Matthews yesterday from Caltech, rightly so. I want to acknowledge as well Harlan Epps, who designed the optical cameras of these two spectrographs, as well as the Deimos spectrometer you heard about in the last talk, as well as MOSFIRE, which we heard so much about yesterday, and is also the designer of the cameras for the Keck Cosmic Web Imager, which will be delivered in the next few years. That would be 5 optical and infrared spectrometers for the Keck Observatory. High dispersion spectroscopy. So, it's unfortunate the resolution. When I tested this, the resolution was high, but hopefully you guys can see this all right. This was a state-of-the-art spectrum with the state-of-the-art telescope before Keck, Palomar 5-meter. It's a very nice spectrum of a distant quasar. Here now is the spectrum, a snippet of the spectrum, acquired by Len Cowie and Tony Sangela of the University of Hawaii, also two great pioneers of this field. Your job is to identify where that snippet is in that spectrum. If that didn't go so well, here's another one. It almost looks nothing like the data from the 5-meter telescope. You appreciate. Truly. This opened up in a complete new view of the cosmic web as we now know it today. Yet a third one. I mean, it's to the point where you might even believe, might think I'm making this up. There is the full Keck high-res spectrum provided by Len and Tony. It's the same quasar, just taken at exquisite resolution. So, that's the backbone of all the great hits on the intergalactic medium that have come out over the last 2 decades. I won't have time, of course, to discuss them all. I'm just going to dig into a handful of these. Let me begin with a topic known as Big Bang Nucleosynthesis. You've probably been told that your body is primarily composed of stardust. This is true. And indeed, most of the periodic chart is also composed of elements that come from stars. But if you were to ask the question, where did most of the fusion in the universe occur, when and where did most of the fusion in the universe occur by mass, the answer is during the first few minutes. after the Big Bang. And we call that process Big Bang Nucleosynthesis. Most of the action was making helium, but there was a few other light elements that I've circled here. Here's the process in cartoon form. Take a neutron and a proton, put them together, and you form deuterium. I'm going to focus on deuterium. I meant to say that. I'll be talking about how we use the cosmic web to learn something fundamental about the universe here. Deuterium comes together to form helium-3. That's an isotope of helium, and helium-3 plus deuterium come together to make that helium-4. It's a very stable element in the universe. But I'm focusing here on deuterium, that first step, if you will, happening just a few minutes after the Big Bang. It's important to note that all astrophysical processes, stars actually destroy deuterium. So if you're interested in studying it, you've got to be away from stars, away from galaxies. Another very important aspect of this is that deuterium serves as a baryometer. What do I mean by that? This plot is showing here, maybe concentrating on the top axis here in terms of this, the x-axis. This is the mass density of the universe in ordinary matter, in baryons, stuff that we're made out of. And what you're just supposed to note is that as a factor, as you change that number by a factor of 10, this number, the amount of deuterium to hydrogen, changes by orders of magnitude. Deuterium is very sensitive to how much matter there is in the early universe, or today. Orders of magnitude. Whoa, there's an equation. Not only am I showing spectra, I'm showing equations. That's a double no-no. Is a double negative makes it a positive, hopefully? The last aspect of deuterium, I'll go through this quickly. These are energy levels of the hydrogen atom. That there's called the reduced mass. It's sensitive to the mass of the nucleus, as well as the mass of the electron. And the fact is, deuterium is twice as heavy, essentially, as normal hydrogen, and that leads to a very small shift in the absorption lines of deuterium relative to hydrogen. And it's that we're really after with the Keck telescope. Okay, so we have found out over decades of effort on this topic that it's very hard to find places in the universe to do this experiment. There's essentially two approaches. One is to get lucky. This is a spectrum where by getting lucky, that means sending a graduate student to the Lick telescope and making him study hundreds of quasars and find the one little patch of the universe where you can do this experiment. David Tytler's group has been pushing this over the last 20 years. This spectrum from Lick gives you an estimate of how much hydrogen is there, but as I showed you, when I didn't emphasize, the amount of deuterium there is 10 to the minus 5 the amount of hydrogen. So you get the hydrogen from this spectrum, but really, to get the deuterium, you need the high precision and the high sensitivity afforded of the Keck telescope. And it's that little blip there, which is the signature deuterium, 82 kilometers per second away from where the hydrogen lies. That's the getting lucky approach. You can also be clever. We've recognized that by going to systems that have far more gas associated with them, you see much more absorption here in the hydrogen. You can also see much more absorption from the deuterium. These are the deuterium lines now, not just blips, but easily identifiable individual absorption lines. We've now measured D, that's deuterium. We've now measured H, that's hydrogen. Over 20 years, there's only still about 10 high-quality observations. Here they are. Put them together, take a weighted mean, you get this value here, 10 to the minus 4.55 or so. And to remind you, we can now take our theory of Big Bang nucleosynthesis, use the measurement of deuterium, combine the two, and get now an estimate of the baryonic mass in the universe. There it is in numbers. The takeaway number for you is that 4.5% of the universe is ordinary matter. Right? And all that comes from the little wiggles, if you will, in the spectra afforded from the Keck telescope. That's not exciting enough, at least not to me. It goes one step further. I've described to you the measurements that we can make with the Keck telescope using deuterium to estimate the baryonic mass of the universe. Completely different teams, hundreds of scientists using millimeter telescopes, satellites studying the Big Bang radiation. We call it the cosmic microwave background, CMB. Can do a complementary experiment. This is a description of that image I just showed you of the cosmic microwave background. Details aren't important. But from the relative height of these two peaks, really that's about all you have to measure here, is the height of that peak and the height of that peak. You get an estimate of the mass density of the universe. Intermediate, completely complementary from what you got from deuterium. There's the numbers. Here's the overplot of the deuterium number. Identical. All right, two completely different astrophysical tests of the same, measurements really, of the same cosmological parameter, how much mass the universe, completely agree. Fantastic empirical result of modern astrophysics. Let me now move to the rest of the elements, some of the rest of the elements in the periodic table. A result that I would say just fell off the telescope, literally, from the first data that were taken of these distant quasars. This is work really pioneered by Tony Sangela. This is, again, a snippet of the spectrum from Keck high-res. None of these absorption lines are associated with hydrogen or deuterium. They're all heavier elements. They're all metals, primarily carbon, some silicon. You can see it there just by your eyeball. Just we're not able to do this prior to the Keck Observatory. We can also, these arrows here now indicate all those arrows are individual carbon absorption systems in the intergalactic medium, in the cosmic web of our universe. I'll also mention something about galaxies, but let me keep on the theme of the enrichment of this cosmic web. Again, each of these arrows indicates carbon absorption in the universe. It's ubiquitous. Any quasar spectrum you take, you'd see it. It's highly ionized carbon, much more ionized than what you see in galaxies. Generally speaking, you would see, we call a carbon or carbon-2, that's either atomic or either neutral or a single ionized carbon. This carbon is triply ionized. It's very ionized. Don't see that in galaxies. Not only that, you can look at the spectra and you can go and find the location where the hydrogen lies associated. So the red arrows here, there's one for each of the blue arrows. That's where the hydrogen lands, hydrogen absorption lands for those carbon systems. And you find that the associated hydrogen is 1 million times lower than what's in galaxies. You quickly conclude, literally just falling off the telescope, that there's gas enriched outside of galaxies throughout our universe. The cosmic web is enriched. It's more difficult to put a number to it, but people have. And you find that it's enriched to about a level of about 1/1000th that of the sun. So the material outside of galaxies, take away a number, would be something over 1,000th of solar. We can do that as a function of cosmic time. This is redshift. There's cosmic time. Big Bang would be here. And you see, we believe, a buildup of metals outside of galaxies over the last 10 to 12 billion years. Here we're combining the optical spectrometers with Keck and some of the near-infrared spectrometers at Keck. Let me turn to galaxies for a few slides. This is some of the work that I've been focused on. Quiz number 2. One of these is a set of absorption lines. If you can't read it, it's magnesium and sulfur, silicon, zinc. One of these is data set from the Keck telescope, and one of these is a data set from the Hubble Space Telescope of our own galaxy. And the point is they're almost identical, because they really look almost identical. The one on the right is the galaxy. The one on the left is a galaxy, just a very distant galaxy, that we can probe in very much the same way we do our own galaxy, just by counting out atoms. Or maybe it was that way. Or no? I can't remember either. For a handful of these galaxies, we can study the abundance pattern. The gray dashed line here, which is a little bit washed out, is the sun. If you can't see it, trust me, it goes more or less through all the data points. This galaxy, which is about 10 billion years old, has an enrichment pattern, has a periodic table, if you will, just like our own sun. That's pretty amazing. And it tells us something about the way stars form in the very early universe. Apparently, rather similarly to the way they form today and have been forming in our own galaxy over the past 10 billion years. We can trace that evolution with time in galaxies. Again, redshift on the x-axis, time on the top. We see a modest but significant buildup of metals, enrichment in galaxies over the past 10 billion years. We can study the kinematics of these galaxies as well to build up a fundamental plane, as we call this in astronomy, of metals, redshift, and kinematics. I left this slide intentionally blank because I knew I'd be running out of time. Some of the most active areas is studying the enrichment of gas around galaxies. We'll have to save that for the next gala. There's metals everywhere. I've shown you examples of gas around galaxies, gas within galaxies, fully enriched. You might ask, is the entire universe enriched? We don't believe it should be. Those same simulations of the universe say no, they shouldn't be. Oddly enough, it's taken great effort to find pockets of gas that are not enriched. Here is one such pocket. Here's the hydrogen absorption. There's plenty of gas around. Again, strong absorption lines from hydrogen. And you're supposed to focus on what is very boring here, no absorption from heavy elements, oxygen or silicon. And that's one of the few pockets of the universe which has a metallicity, an enrichment level, say 10 times less than all the other stuff I've been showing you. Something approaching what we expect to be primordial, consistent with the lack of heavy elements at the start of our known universe. So, probably not the entire universe being enriched, but most of it, at least most that we can detect. For the last few minutes, let me come back to the cosmic web. I showed you this lovely output from a computer simulation of the web. I'd say one of the reasons that the theorists and myself am confident in showing a picture like this of the universe, again, is due to the fact we can probe it and have probed it in absorption, cannot do it in emission. The idea, again, being a distant quasar intersecting this patch of the universe to our telescope. We can simulate in the computer the absorption features of that cosmic web, and we can detect directly with the Keck telescope the absorption features. Here's your last quiz. One of these comes directly from the Keck telescope. It's 18 years old. And one of these comes from a numerical simulation of the universe. It's 3 years old. I will take 2-to-1 money on anyone that wants to bet that they know which one's the computer simulation. Come on by after the talk. I quizzed 4 of my colleagues. They went 1 for 4. You're going to have to pay to play. So, simulations like those, let's just stare at that again. Simulations compared to data like these really lend strong confidence in this paradigm of a collapsing cosmic web universe that come out of these simulations of this so-called CDM cosmology. And taking it a step further, we use this data. This is the mass scales of mass in the universe. This is the fluctuations on those mass scales. We use these data from the cosmic web to constrain CDM. Not only, I'd say, prove the existence of CDM, but it also can be used to constrain it and test the cosmology yet further. Again, first pioneered by the Keck telescope. Fantastic work. And with the last 2 slides, if you're like most astronomers, you really want to see to believe that this cosmic web exists. We're pushing on that. It's very difficult. Here's a putative example of it. I call it the Slug Nebula. It's a very deep 10-hour narrowband image taken with the LRIS camera on the Keck telescope. At the center here is a quasar, and we believe that this quasar is lighting up gas on scales of 500 kiloparsec physical. That's 1.5 megaparsecs co-moving. It'd be something of order that little box there in my cosmic web diagram. Perhaps putative evidence for a direct image of the cosmic web. I'm sure there were scientists in the room that will quibble with me, and they should. I don't believe that necessarily. If I want to prove that statement, or at least provide much greater evidence for that statement, we need to take spectra. The image is nice, but we need to confirm how the gas is being emitted, how it's moving about with spectroscopy. We'll try with the current instrument suite at Keck. But truth be told, I am really, really eager to see this Keck cosmic web imager, which will allow us to take spectra out of all these little squares, as you see. They feed the instrument. The PIA, Chris Martin, is here in the room. Support him, please. And the idea will be to both image and take spectra simultaneously of phenomena like these, ideally, so that when I come back 20 years from now, instead of showing you images of the cosmic web from a computer simulation, I'll be showing you the images of the cosmic web from the Keck telescope. Thank you.